Here is another acid-base equilibria problem. Again, we can solve it using pKa values, where we're going to look at the acidity of the hydrogen on the acidic portion, the acidic molecules. There's going to be an acidic molecule on either side. Some are more acidic than others, of course. So the pK of water, if we look at table 13 or 3.1, is 15.7. And the pK of this amine with a hydrogen is really not indicated on the pKa table, but we can assume that it's around 38, which is third from the bottom on table 3.1, and it has ammonia as the molecule, but this molecule is similar to ammonia in that it has a nitrogen with a NH bond. And so, of course, the higher the pKa value, the lower the acidity, and thus the left or the right side here will be favored at equilibrium. And again, we can see that there's about a 22 pK unit difference. There's really no equilibrium here. It goes fully to the right. So this base here, this nitrogen with an anion, fully deprotonates water, creates 100% of this amine here and 100% of the OH minus. And if we think about ARIO again, it comes down to atom. We have an oxygen with our anion, and we have a nitrogen with the anion on the left side. And again, the O is more stable as an anion than the N is, according to the atom argument. The O is more electronegative, and so we would circle the right side of this acid-base equilibria. There's another question we could ask ourselves. What if we were given a picture of this same amine, but we were asked, is water a good solvent? Can I put this amine, or I'm sorry, this amide, this is a nitrogen anion, can I put it in water as the solvent in order to undergo some other reactions? Basically, will the amide survive being dissolved in water? And so what you should do is set up this equilibria that we just discussed. The amide plus the solvent that you're proposing produces two other compounds, the protonated amine and the conjugate base of the solvent. In this case, it's OH minus. And we just decided that the equilibrium lies far to the right, almost exclusively on the right. And what that means is if we take this amide, mix it in water, we're going to end up with this stuff here. We're not going to have our amide anymore, and thus whatever reaction we wanted to do with this amide will not occur. So H2O is not a good solvent. So if you're asked, is this a good solvent, or should I use this solvent with this reactant or this base? Really what we're asking ourselves is, it's a different way of asking this acid-base equilibria question. So write out this equation and ask yourself which side is favored at equilibrium. That's how you decide if whatever is proposed is indeed a good solvent or if it's a poor solvent. In this case, water is a poor solvent.